Hey, what's up? Welcome back to Advent of Code. Day, what was it? 23, a long walk. And it's been a long walk indeed, because the thing that I started running yesterday hasn't finished running. I didn't leave the computer on during the night, but I mean, I closed the lid, so I think when you do that, everything gets suspended. But in any case, this is not finishing anytime soon. So it's either like looping and never going to finish, or it's just going to take a very long time. In any case, it's way too slow, and I don't even know if it will reach eventually like a good answer. What is this? This is the code of the library that I was using for this shortest path algorithm. But yeah, okay. I have been thinking about this for a bit, and I think I want to try doing something different, of course, because even the solution for part one, if we run this cargo run, so for the sample it runs okay, but for the actual input on part one, it's already taking quite long. Actually, I should kill it and let's time it. Yeah, kind of like this, but do it with this. But yeah, it's taking, I don't know, like many seconds to run part one. So it's already too slow. So there are a couple of ideas of what we can do. The most important one, I think, is to reduce this graph to something more manageable, because what we have is, well, a giant, here we can see it printing before, like a giant maze that doesn't branch too much. So it's like it branches every now and then. Like you can see that the first path that you take, only here it branches. And actually, now that I notice it, was this always the case, that the slopes are just around the intersections? I didn't notice this before. It kind of looks like it, and I feel like an idiot for not noticing that. Well, that's definitely a side effect of looking at things with fresh eyes. But yeah, also in the sample, it seems like the slopes are only on the intersections. How did I not notice this? I'm quite blind. All right, so yeah, and what's happening with the slopes on part one is that you cannot cross a slope. Like for example, if you're here, you can go in this direction to the right, because when you step on this slope, you can only go to the right, or you can go down, but you cannot go left. So it basically restricts some of the paths that you can take. And I think it probably makes I'm not sure, but also all the slopes go down and right. So kind of like they take you in the direction that you need to go. And I sort of suspect that makes this graph like acyclic, like it doesn't have loops, I think. And maybe that's the reason why this thing, our approach, worked for part one. We can see how much it took to run, like 50 seconds almost, which is quite slow. But yeah, these conditions here, like of going up and left, are not necessary to check actually. And yeah, I just noticed that the slopes were around the the, how do you say, like the intersections or bifurcations, I don't know how to call them. Okay, that's good to know. That's good to know. So what I was thinking, at least that we can try, is to try to convert this grid into a graph where we have nodes, like this would be a node, the starting node, and this would be a node, the ending node. And then like these intersections would also be nodes, right? And yeah, it's much more easy to see now that I see that like the intersections are surrounded by the slopes. But yeah, and then walk the grid and build the graph from that, and then work with the graph. So like this node will be connected to this, and it will be a directed graph. So if this is connected to this, there is like an arrow from this node to this node. Doesn't mean that this one is connected to this, because in part one you cannot go from here to here because you cannot cross this. It wouldn't also make sense to go back to the start, but you can think about that for other cases, like this one, if you follow along, is connected to this one, but this one is not connected to this one. Like the other way is not true for part one, but it will be for part two. But yeah, just changing these to a graph will drastically reduce like the size of the graph, because basically right now we are working with this grid, but we are calling this algorithm like it's a pathfinding algorithm, but we are considering each tile a node on a graph. So the final graph is gigantic, or well, pretty big, whereas the intersections are much fewer. So that's the first thing that I would like to try, just convert this into a graph and then have the same approach but working with that graph. I would expect that to work really well for part one at least. It should make things much faster, I think. But I don't know if it would be enough for part two, because also this algorithm, it's a shortest path algorithm, and that's not what we want. We want a longest path. So we should probably do something different. So okay, let's try to do that. So where do we start? Let's remove some of the gunk here that we don't need, because we know that this is a condition that never happens. Going up or left is also something that doesn't happen. The printing of the grid was a nice idea, like it's cute, but I don't think like we can do that for, let's do it for the sample maybe. So if we run this with a sample, it should run, and if we run it with debug 1, what? Oh, I just run it without the time. Yeah, it prints the path, which is really neat. I really like this, but I don't know if we are going to do that. Like, if we work with a graph instead of with a grid, it's not going to be easy to convert one into the other, I think. So maybe we will lose the printing. Okay, and also probably this, I want to just use it, ensure. Yes, use anyhow ensure. Just cleaning up some things. Okay, and I would like to then, as path length, I would like to extract all of these. Like this thing should leave, let's put it on a function. I don't know, find longest path, and this will just return the longest path length. at the end, let's also put this commented code here. I mean, I'm not going to use the commented code, right? But anyway. Okay, shortest path. Yeah, this thing should return, let's say, a result of, I don't know what is this type, longest path length. Like the cost of this. Oh, we are using i32 because I guess this here is an i32. Well, and we also need the grid, of course. So let's pass in the grid, which is just going to be something like this. And let's say, let's longest path length is find longest path of this grid, whatever. This will be then, I don't know why I'm sketching this out so much, because it will then have to take the graph to work. Your problem here is, oh yeah, this should be an okay thing. Yeah, this unwrap here is unnecessary. Let's do a context from, like, expect this thing, and if it fails, no, I don't know, no paths found. So if this max by fails, it's because no paths have been found. And the width and height, yeah, let's put it there just so it doesn't complain, but I mean, it's not really necessary. And with this, we can propagate errors up, and things should work the same as before. Even the debug printing. Now, why did the debug print? Oh. The problem here is that what's your problem here? Oh, this is a reference. So dereference, I guess? We were already dereferencing here, right? So this is finding k shortest path. Well, we can do into iter, and now why? Why are you still a reference? Well, I don't know, but just the reference and don't complain. Okay, let's think about building the graph now. So, what are we going to do? We're gonna have a start and an end, which are basically, well, here we are checking the end, and this would be the start. I would probably extract this. So yeah, let's say let's start be this. I don't know if the explicit type is needed. Let's not put it for now. And the end should be something like this. Let end be so x should be width -2 and y is height -1. This is where we want to go. I think we are going to need this to build up the graph, because we want to start at the start and we want to finish in the end. And I'm probably going to do like breadth first search or depth first search, I think is kind of the same for this, but yeah, kind of walk all the, do a similar walk of what we are doing here. Yeah, but kind of a, I don't want to do recursion, so like an iterative algorithm like breadth first or depth first, something of that sort to build the graph. So actually I want something similar to this function, but just call it build graph. It's going to take a grid, of course. It's going to return a graph, which I don't know what it will be, and if it may fail, let's just have a placeholder for this. Let's call build. Look at that, there's a build path on the path finding crate that we are using. But we're gonna pass this thing. I guess we can also pass the start and end. Sure, why not? Start, end, right? I don't know if I want that or if it's too much. If we have the graph, well, we're still going to need to know where the start and end. Well, let's not parameterize this more than necessary. So let's hard code. Like these things are going to live inside here for now. We can think about later. We can later think about what it makes sense to pass or not pass. The graph, what do we want to make of it? Well, a simple definition for the graph could be something like a hash map that takes a point and gives you back like the adjacency of that point, or like the connected points to that, something like that. And well, a point is just going to be, do I want signed integers here or just use usize for everything? This could be one definition of the graph. But I think once you build the graph, it's like we're going to work with this data with points when we are traversing the grid. But after you have connected all the things and make the graph, the points themselves, I think, are not necessary anymore. You can just convert everything to indices. So like you have the hash map, but you know, you can have something of this shape inside of here, but then what you return can be a linear vector of vectors of indices, and you know, the nodes are just indices on that vector, and simplify you know, the data structure, and make it also like more memory friendly and more computer friendly. But okay, we can probably work with this for now. All right. So how are we going to do this? Well, we are going to have some sort of queue or stack to process these things. What was the difference between breadth first and depth? Basically, like the difference of those algorithms, breadth first search and depth first search, is whether you use a queue or a stack for them, and which is which. Like I think if you use a stack, you are going to go depth first, because whatever you push, like you visit some things, you push them all into the stack, and the next thing that you are going to pop are the last things that you visit. So you're going to get deeper and deeper as you go. Whereas if you used a FIFO or a queue, you push the first things that you see, then you pop from the front. So the first thing that's, the first things that you have pushed are the first things that come out, and you're going to see deeper things, but the next thing that you pop is going to be also like a not so deep thing. So you're going to cover breadth first. So I'm pretty sure that breadth first is a queue. Does it make any difference for this case? I don't know if it does. So since I don't know if it does, let's just simply use a stack, which is simpler because it's going to be a vector. So let's say let mute, I don't know, and visited, whatever. It's going to be a vector, and we're going to start with our start node. And we're going to have this as the queue of things to process, but then we also need to have a graph that we're going to be building. So let's have a graph be a hash map new, and in the end we're going to just return this graph, and then we're going to have our usual popping things from the stack. So let's what is this? I don't know, XY basically. In unvisited pop, we have to process this. So let's go to the sample and think about it for a bit. So we're going to start here, and I think, what are we going to do? Basically, well, the start is kind of easy because you only have one direction, but you can think of, we are in a node, we are going to reach here. And so imagine that we pop this node. Basically, we should look in the 4 directions and start walking in the, well, according to these rules. So some of these directions are going to be unwalkable, if there is a wall or if there is a slope that you cannot cross. And well, then loop and walk until you find something else. That's basically what I think we should do, right? Yeah. Should I also I wonder if I should put in this unvisited or well, queue or stack, whatever you want to call it, the direction that you're starting. So we are starting from the start and going down. That will be the start thing. And if we did that, then whenever you get into an intersection, you would push all the directions or the valid directions to process, and just end the walking there. And so, yeah, that kind of seems reasonable to me. Although it's not necessary, right? Let's try to not think about that. I'm not sure of how to start here. Something, well, we're gonna have the directions, that's for sure. Let's copy this. It's gonna be a similar idea to this, I think. So we're going to walk in each direction. Right, and once we start walking, like what I think I'm like starting with the directions, I think the problem will be that we're going to sort of repeat the direction logic to like keep walking. Yeah, I kind of think so. Let's see. So let's sketch it out for dx dy in directions. I don't know if I want to consume this, but we can copy, of course. We're gonna probably do something like this. Although, well, we do the wrapping add, that's, yeah, sure. We're gonna get the tile, but what are we going to? Here we were like short circuiting from this. If we cannot get here, instead of short circuiting, I want to like ignore this direction, I think, because this is basically only caring about the case of when you start, you cannot look up. Yeah, it's kind of stupid to think it this way, but I don't know. But basically, I want to do get and then is what I want. And then row get nx, and let's say let some tile be this, or else just continue, right? Your problem here is what type annotation? What is and then? I think I wanted map. Is map what I want? Maps an option to option. I think and then sounds a bit more like it, because the thing inside returns. What's your problem here? X and Y. All right, let's put some types on the start. Yeah. So now it's not complaining. Type inference is hard. So sure, tile is a char reference. So if we go out of bounds, we just ignore this direction. Sure. How else are we going to ignore this direction? I think we're going to do something similar to this, right? We sort of want to loop and do this, I think. Right? Kinda. So these are the 4 directions that we want to check. But actually, once we start walking into one direction, we should keep going. Like, that's what I want to do. And in order to keep going, I think what I want is like sort of a previous position that would be xy at the start, and then like a next position which would be xy plus dx dy, and so you can keep looping and not going back. Something like that. Right? Seems like it's How do we walk? That's the question here. Because we are not like fluid feeling. It's an x and y. I'm having trouble thinking about this. You get a direction, you have like a next thing that you want to move to. So then what? You could have like neighbors. The thing is, what we want to do while walking is to like keep walking until we reach the end, or until we see that, okay, like imagine we are here, like what do we do? Basically, if we are here and we come from here, we look at the 4 directions that we are, like 4 of our neighbors, and if only one of them is valid to walk, so that means it's not a wall and it's not the previous position, then we go there. Otherwise, if many of them are available for, like in this case, when you reach here and you come from the top, you will have 2 different neighbors. That is a special case that we are going to put into the graph. I think that is kind of what makes sense to me. Right? I think so. So, right? It kind of makes sense, I think. So I think we actually want to have the direction here. Right. At the start. Yeah, because I'm sort of thinking this in a weird way, I think. Let's follow that hunch and say, okay, we're gonna start from the start going down, and going down means x, like dx0 and dy1, basically. That's what we are going to put in there. And well, we could put that, or like the next position. It's kind of equivalent, I think. Sure, I think it's kind of the same, so let's assume it is the same. Let's call it also dx dy, and I probably want to have some of these things be mutable. So okay, that's what we want to do, like start walking from here in this direction. That's what we want to do. So, and we are going to loop here. I'm not sure how, but we are going to loop. The next position then is going to be this, and we can check the grids, and I'm moving more things that I wanted. Right, we will check the grid in that direction. If it's not, well, continue, no, like break, because we are in a loop now. So we're trying to walk this loop. We're also going to need to count steps, but let's think about that later. So okay, if we have a tile, then we're sort of walking there. What are we going to do next? How difficult it is to think about walking a freaking graph. Then we can do, I guess, this thing. If you can walk this or not. And x and y is, yeah, this is correct. We could have the neighbors and check, yeah. Let's actually maybe not think about the slopes first, because I'm going to get confused by that. Okay, like this is the next thing that you want to walk. In the beginning, like starting dx dy and x do I want to do that? How difficult could it be to walk? We'll have a position and a direction. Okay. Yes, and this is the next x, next y. Sure. So we're going to walk into here. These things are surely going to be mutable because we're going to be changing these. But anyway, the tile, do we want to know the tile of this? I don't know if we want to actually, or if we want to check all the directions and then there do the tile checking. I think that makes a bit more sense to me. Right, so we are kind of walking from this position. Yeah, okay. Okay, I think I got it. I think I got it. What if we think about it not in terms of a starting position and a direction, but in terms of like a position and previous position, something like that. And if we do that, yeah, I think that will simplify things a little bit. So the start is 1 0, then it's going to move to 1 1. Okay, so let's say that this is like previous position and position. Something like that. Okay. Yeah. So position must be valid, and I guess previous position also. We know that in the start that's true. I don't think we need to worry about weird edge cases. Yeah, no. Let's not worry about that. So we are in position and we know where we are coming from, the previous position. And then we are going to loop. And in order to loop, yes, we are going to look in the 4 directions, I guess. Right? And what we are going to do, we're going to have the directions. We can basically map these directions to the neighbors and to whether you can walk into them or not, something like that. Yeah. Let's do that. So let's say, well, these are the directions. So let's say simply something like, let's neighbors be there's, I think you can map here, right? Yeah, because this is a static array, which is nice. I don't want to do stupid allocations. We're gonna map each dx dy to basically something like this, nx and y, and so what do I want to map? I think I want to map basically to optional positions, and it's gonna be none if you cannot move there, or some if you can move there. Right? That sort of makes some sense. Yeah. Why not? So let's put something like this. It's not break here, so instead of saying break, we are inside of a map. We're gonna just return none in this case. Woohoo! And actually we can probably, well, do something, but if everything goes right, we are going to say nx and y. These are going to be the neighbors. And let's say, I think these are going to need to be mutable, but x and y are going to be position, and I don't know if we need priv x and priv y, so let's keep it as x and y are our current position. And you don't like this because who doesn't know its types? Come on. Previous position and position doesn't know what it is, so let's put some types in there. Okay, So if it is out of bounds, there is no neighbor there. If the tile of the neighbor is this, no neighbor there then. And also let's say if nx and y is equal to our previous position, then also this is not gonna be a neighbor. So we don't walk back. And then finally I want to filter by tiles. So I think this condition should be all right. If the tile is down and our direction is up, dy is -1, then we say none. And that makes sense. We cannot cross that. Yes, that makes sense. And the same for right slope and going to the left. So this makes sense. So now we should have an array of 4 neighbors that are optional. Sure. And we have some different cases here. Basically, well, there is one thing that I haven't checked, which is what happens if my only neighbor is the end. If that is, or if one of the neighbors here is the end. If that's the case, then we should well, special case that thing. Why is this so difficult? I don't know, but previous position. Okay, so now let's process the neighbors. We want to say something, I think, like, do we have, I don't know if we have any dead ends. So that's something to check. So the interesting cases is if we have 0 neighbors, 1 neighbor, or more than 1. Those are the interesting cases. So yeah, let's write about that. If neighbors, let's actually switch maybe, match neighbor's length and 0, a 1, and anything else. So 0, I don't want to, I think this should be unreachable. Dead ends. We should probably change these to error propagation f, but for now let's make it panic. I don't care about that. If it's 1, it's an interesting thing. It's like we keep going in this direction unless it is the end. So if it's 1, can we destructure from here? Oh, we are asking if neighbor's length, but actually this thing is a static array, so the length is always going to be 4. That's not what we want. We want to ask how many of them are sum. So how do we do that? It's kind of annoying to check, but to check and then have to find it again. But I don't want to do an allocation, so let's go with that. We're just going to say iter filter is sum and count. Just that. Yeah, so if it is only one neighbor that we can visit, that is the walking code. So say let neighbor, I don't know, nx and y. It's gonna be neighbors find map, right? Kind of, we can just do this, I think. Find the first one and wrap should be neighbor here is this, return this. Yeah, and wrap should be safe here because we know that there is one that is sure. Not the prettiest code, but eh. Okay, so this is the neighbor x and neighbor y that we are going to walk to, but we can also ask if this is the end. We can ask it here, or we could ask it at the beginning. I think either case is kind of fine. So let's here just mutate and say the x and y are going to be nx and ny, and our previous position is going to be x and y. So previous position is going to be x and y, and x and y is going to be this. So we're going to have this thing be mutable, and we're going to have these two things be mutable, I think. Does that make sense? I don't know, but we shall see. And let's put somewhere like when we find the end. So is it when we are looping? Yes, it makes sense to be here. So let's say if x and y is the end, then I don't know what we are going to do, but we are going to for sure break out of here. And I think the end is basically kind of the same condition as, or a similar condition of finding an intersection, but let's just put into the graph. We're going to insert, well, basically this means the node that we started from is connected to the end. So that means, well, are we inserting? I think what we actually sort of need to do is get me the entry for this thing that we are visiting, like the original position. Or is it the original previous? Oh, I think it is the previous. That's kind of weird. Let's actually separate the mutable things from the immutable things, because I'm going to get really confused. So we state that we started from well, from the start, and this is one less than the start, one down from the start. So let's call this first thing like actually node. This is the node that we are on the graph, and this is like the next position. Let's call it node position and next position. X and Y. So let's also have a mutable mute ref previous X and mute previous Y is gonna be, or well, we call this thing pre-position. I think we can not this structure, but let's have the mutable things like this that we destructure here. Let's keep it at that. Pre-position is going to be node position at the beginning, and then X and Y are going to be the next position that we extracted from here. Great. And then everything else I think keeps being the same. We compare in here and we are assigning that, so that looks nice. But now we want to say position, yeah. So with this loop, we're going to be starting from the node. So let's make sure first that the entry for the hash map for this node exists. So graph, I want to get the entry for node position, and does entry receive, yeah, it receives the key. Or insert an empty vector. So we know that it is initialized. And then we can just access it, I think. So we can say something like, if it is the end, then graph at node position. Can we do this? Push the end. Can we do this? You expect a reference here, and you cannot borrow oh, insert or get mute. Yeah, okay. So I guess get mute and pass in the node position. This should not complain, so okay. We reach the end, we break out of this walking loop, that is fine. Then if we have one neighbor to walk to, we walk to it. Great. And if we have many, this is also the important one. This is the important one. We are going to sort of do this again. Maybe we can have this into an iterator that we copy or something, but we are going to loop over these neighbors and push basically. We know, so if we have many, we know that we are in an intersection. So it means that this node, where is it? Node position is connected with this intersection. So we push that into the graph. So actually the position that we are currently in is the intersection, because we looked around, we looked around XY. So XY now is an intersection. Yeah. Yeah, that's cool. So there are many. We can then push this into the graph. So do something similar graph, similar to what we did here for the end. We're going to push XY. And we are not checking, like this is probably, we are going to need to check for repeated things on the graph and things like that, because otherwise I think we're going to loop around or something. But let's not think about that. We know that this node connects to here, and actually we are missing counting the steps. So the graph should have also the steps, because otherwise, like the length. Otherwise, this won't work. But then after this, we are going to iterate over this and push to visit this. So for nx and y, or for neighbor position in blah blah, we are going to push to the unvisited to keep visiting from this intersection to the different places. So unvisited, push, and here we had the position and the next. And so the position is going to be xy. So start from this node, and the next is going to be neighbor position. And here neighbor position is, oh, it's an option. So let's, here we are filtering. We can always filter map here. It says filter map, right? And here we are also going to do the same, filter map. Yeah, right? This thing can map, but it cannot filter map, I think. No, it can just map. It's actually, I want to have this kind of in a variable. Let's call it valid neighbors. And we cannot reuse it here, I think, because it's going to be using a moved value for sure, but we can clone it. And here we can sort of use the same thing. Valid neighbors, the first one basically. Or have just simply be next and wrap. And of course, you're going to, well, what's your problem here? You cannot mutate. Well, clone maybe? Yeah. All right. So is this the logic? I have no idea. It turned out to be much more code than I imagined, but we're gonna have the graph. And we're still missing counting this thing. So okay, the graph should be from a node, these are your neighboring nodes, but with some count. So let's put it as, I don't know, usize. Does it make sense? Or 32-bit integer, I don't know. I'm using usize for kind of everything, so let's keep using like the number of steps. Let's actually use a smaller integer for this, something that makes sense in my head. And okay, when we push things into the graph, let's call this thing graph, or let's declare the type so it fails. Okay, we need to count the number of steps. So besides this, we are also going to have let mute steps be 0, I guess, or 1. I don't know how we're going to initialize this, but we're going to push this. I think it should be started at 1, but we shall see. Here also we need to push it's connected to this with steps. And when we walk, we're going to increment steps. All right. Horrible code, but will this work? Let's print line this graph. I don't know. Well, let's just run it and see what happens. By the way, did I kill the running of the... No, I didn't kill this, so this has been consuming my CPU for a long time. So yeah, it's been running for almost 600 minutes. That's great. 10 hours? Only 10 hours? Well, okay. Let's cargo run. Let's not run in release mode because I want to know about overflows or things like that. Let's run with a sample and see what we print. We have a lifetime thing. What's your problem? Cost here. If you dereference this, will you be happy? Longest path is not used. Don't use it then. Well, maybe we got into an infinite loop. That's interesting. So, how do we debug this? Unwrap or default? What? It's... But I want to insert. Well, okay. What can we do to debug this? Let's print line here when we're starting. Starting the walk from node boss. So we're starting from there, but we never break out of there. So that's great. Oh, by the way, did I break here? Oh, yeah, here we need to break in some cases. When we walk, we keep going, but when we do this, we should break. We should break out of this loop and the walk. So was that the problem? Oh, look at that. Now we did finish. So we are starting the walk from these different places and we are having a nice graph made. That's awesome. So does this graph actually make sense? Well, maybe we can print this graph not like this, but I think this is not going to be, no, this is not a nice printing. So let's do for key value, yeah, in graph iter. So the key is a position, well, it's going to be connected to, and just the value. Okay, that's okay. So 1, 0, the start point, let's take a look at the sample, is connected to 3, 5. So yeah, x3 and y 0, 1, 2, 3, 4, 5. Good. With a length of 14. Now, is that correct? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think it should be 15 or even 16. I'm not sure if I counted correctly. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, I would say at least 15, if not 16. So the walk should probably start at 1. I don't know if more than that, but maybe we can take a look at some of the smaller, but no, all the walks are pretty long, so that's annoying. But well, we have the graph. That is, it seems like something in the graph. 13, 13, is that the end of, no, the end should be at 23 or 22. So is this, yeah, and column using, like, this is the end node, I'm pretty sure. And surprisingly, we are reaching the end node twice? 3 times? That doesn't seem good. So we are repeating things, which is wrong. The end node appears on a bunch of them. Huh. What is happening here? So to the end node 5, 13. Why is this happening? So let's take a look at 5, 13. 5 would be column 6 here, and 13 is row 14. Is from here, it is reaching the end. So can we go to the end? Well, yes, if we follow like this, we do reach the end in 53. So maybe this is correct. It just looks bonkers. But this one that repeats stuff from 13 and 13, so it's here, it must be this one, right? Yeah. So it does have 4 neighbors, and the 4 what? This one is not right. 13, 13. Wait, when we push things, no, it's not pause, and we push where we are. So we reach, I think we are being overzealous when we push the end node, but is it able, like maybe different things are reaching 1313 from different positions, and then we are walking from 1313 till the end, but I don't understand why. Maybe we need more printing. So we started the walk from 1313 4 times, and the 4 times we ended at the end. That's really interesting. So if we start here and we go down, for example, we do get to the end, yes. And if we go right, I guess we are going to see the same thing, because it's like we cannot go to other places. Yeah, we go. Okay, so we do get to the end. And is it repeated? So it's 24, 32, 24, 32. Yeah, okay, we are repeating that. We are repeating that, which is not good. Okay, so I think there is a simple solution for this, which is, if we already know about this node position here, we should break, right? So let's do what do I want to do? Basically, I want to do something like this. Let's some node be this, or else, well, no, basically I want to do the contrary. If it is none, if it is some, then we break. That's what I want to do. So let's write it the stupid way. Well, not the stupid way, but the match way, like explicit way. If there is already some node here, we continue processing other things. We already know about this. And if it's none, then I want to insert, right? That is kind of, yeah, kind of it. So probably should use, does the OR insert do this? Ensures a value. Inserts if it's empty. Can I do and modify? Can I ask if I'm complicating things a lot here. Let's just do a simple if condition. If graph has key contains key and just pass in the node position. If it already knows about this, then continue. That's what I wanted to do, just that. If we run now with the sample, we should, this looks too sparse for a graph. Oh no, it's not just that. It's more complicated. It's more complicated. Yeah, the problem now is, okay, the logic that we were doing at the beginning, like walking in the 4 directions, had its, we shouldn't ask just for the node position, but like what direction we have seen. So how do we avoid, this is not what I want to do. This is not what I want to do. But if we are walking from this node position into a next position, and we reach, when we reach something, I think it is over here that we want to not push the unvisited. So we have walked in this direction and we reached XY, which is an intersection. If we already know about that intersection, we shouldn't push it to be visited. But how do we know if we know about it? Well, if it is on the graph. But it can also be like not in the graph, but be on the unvisited things. So it's a bit ugly. So maybe let's change the hash map to be something else. This is kind of ugly, but I'm just going to have a hash map of points and cost. Kind of like that. That's the value. So here we should insert a hash map new. We're not going to push here, we're going to insert and steps, and here do the same. Okay, if we run now, okay, that's more like it, I think. I think that looks more promising. Finally, we do have 5 intersections, I think. Well, it's actually 4 and the first node, the start node. Yeah, this looks more like the sample. I think we have seen on the sample that there were 4 intersections. So it's this one, 1, 2, 3. Well, we have more, but actually some of these intersections don't work like intersections, because if you reach, for example, this one from the north or from the left, it's not like an intersection, it just keeps going, which is interesting. So the ones that actually bifurcate are this one, 1, 2, 3, and 4. And this one doesn't bifurcate, and this one doesn't bifurcate. So yeah, it's 4. Okay, with all of that, all of that mess, can we now change? Like, this is a very messy code and I kind of hate it, but let's not look at it, ignore it, and see if we can find the longest path, but now work with the graph instead of with grid. So here I'm going to say let graph be this, and pass in the graph, and this thing we will take a graph, and actually it should take start and end. So let's pass them in. Does width and height gets used? No. Okay, we can move this out again to the main. For building the graph, we're going to pass the start and end. It's all right. Start is a point and end is a point. This is kind of ugly here. This is really start x and starts y plus 1, right? Yeah. And I think since now these are actual points, we don't need to declare this. And then now find the longest path also should take start and end. Okay. We don't need this. And we are not going to do the walk here. So we're gonna start from the start. We're gonna end when x and y, so basically a position, when positions equals the end. We are not going to do any of this directions thing. What we are going to do is to just access the graph, I think. So just say graph get x and y. So here it's a position, what we get the neighbors at this position, and then what are we going to do? This is going to be a hash map. So we're going to say, and then neighbors or nodes, I don't know, nodes, sure. We are going to have the nodes iterator. I think I probably want to, this thing should be an iterator. The iterator of this has a position and well, not and then map maybe. The iterator of this has a key and value. The key, yeah, there should be the two, kind of like the tuples that are needed here, but I'm not sure if, well, the mapping and thing is what we expect. It expected a tuple usize option Yeah. Can we flat? Isn't there a flat map here in? No, it's kind of. And then, what is it that I want to? Because pretty sure that this can iterate. Wait. I'm doing things like more complicated than they need to be. So let's do just simply let nodes be graph blah 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 get and wrap. Like if it fails, I don't expect this to fail. And then just have the nodes iterator, I think. Wouldn't that be great? But you don't like this because these are kind of references. Can I have a copied iterator? Almost. Expects a reference, but it yields this kind of thing. Well, you know what? Just give me this position and count or weight cost is, I think. Can't we just like the reference here? Yeah, there is something that I don't know how to do in Rust, that is to convert, but this, yeah, okay, now it's not complaining. Okay, great. If we run now, we do have still problems, because this should give us the shortest paths. Sure. Oh, the costs are of another type. Sure, make the type. Oh, did that work actually? We do have a 94, which is the correct answer, and we changed this to use the graph. That's awesome. So what happens? I am a bit hesitant to run with the input, but I mean, that's what we came here to do, right? So let's actually run this with the input. We have a bigger graph, but was this the correct answer? Yes, it is the answer for part 1, and it ran just much more faster than the 50 seconds that it was taking before. So this is kind of promising. This is kind of promising. That's great. So we're going to, well, we're not going to print anything anytime soon. This is fine. Find too many paths. Sure, these are fine too. So this is already an improvement over part 1 that we had. If we run now, well, now we are printing some stuff here that I don't want to print. But if we now run check all, I think we should have now something that runs before the death hit of the universe. That's nice. Okay, So now we have to try. I don't expect this to work nice for part 2, but we have to try. Let's actually hard code. Basically, what we don't care about are the slopes on part 2. We don't care about the slopes. So for part 2, it will be a matter of doing this, and Clippy wants to convert this to an if, sure, but let's run now. Well, let's run first with a sample, and it panicked. Dead end. Oh, we reached a dead end. Where is it? At some point we are reaching a dead end. Well, let's print it. Dead end at X and Y. How are we getting there? Oh, we are getting back to the start. Going back to the start. What a great song. Okay, so it makes sense. We are getting back to the start. How do we get rid of that? Or do we care about that? Do we care about that? Maybe we don't. If we reach at the end, it's like, maybe we don't care. Let's not care. Let's dead end, but do nothing. What would happen then for the sample? It keeps going. Oh, no. We should break here. Still, it's not doing what we want. We are breaking out of the walk, but are we hitting this thing? Prints line and break. Yeah, we are hitting this consistently. So what's the problem? Why are we hitting the start again and again and again? We should be breaking from this loop. Thanks for the highlight. Yeah, let's bring back some print lines. So start walk at node pos, and we are walking to next pos. And these are debuggable. Woohoo! Look at that. Yeah, we need some end conditions. So when we know about stuff already. How do we do that? How do we do that? Start walk at. Yeah, I have an idea. So yeah, Clippy, don't bother me with this. It's annoying, but we were trying to like early terminate here if we already have if we already know about this node. I don't think that is correct, but what we can do is when we push the node to be processed, So, okay, when we reach an intersection here, we are going to be pushing into the unvisited all the directions that we want to go from that intersection. And that is all the things that we want to, like that's all the visits that we want to do for that intersection. We don't want to do more. So if we reach that intersection again from some other path, we don't want to do this again. So I think here would be a good idea to early terminate and say something like null position, insert this. So we are reaching this. And we can say something like if graph contains key, if it contains the key let's ask if it doesn't contain the key. If it doesn't contain the key xy, we are going to insert at xy a new hash map. Okay. And also we are going to visit it. Otherwise, if it contains the thing and you want to, what's your problem, Clippy? Come on. Oh, entry. Oh, if it is vacant, blah blah blah. But come on, this. Can you allow this shit? Okay, yeah, don't bother me about that. So okay, if it doesn't know about this thing, now we know about this thing and we visit it. And that's great. That is great, I think. It won't, I'm not sure if this is exactly what we want in the case for part 2 where we are ignoring the slopes, because like if we get to, I don't know, to this intersection, for instance, from the left, we want to be able to walk up, right, and down, but also we want to be able to know what is, like it should be a bidirectional graph, I think, on part 2. Let's not think about that for now. We will see if we get what we get when we get it. But if we do this, then we shouldn't need to insert here. The entry should exist. And the graph should start from let's start with a start. So an entry for start and well, let's make a new one and then just insert here. So graph insert start hash map. Okay, so we know about the start. what happens if we run now this part 2 with a sample? 154, that is the correct answer, I think. For part 2, yes. Okay, this is promising. So what, I don't know what will happen with the actual inputs. Let's run this thing in release mode and, ooh, found too many paths. Found too many paths, and the K was 100,000, I think? No, it's just 1,000. So let's bump it to 10,000. And it's taking more time. Why does it scale up so badly? Now I'm feeling like running for K1000 was pretty fast, but for 10,000 it gets like I'm feeling that we might be getting into some infinite loop here. Interesting. But okay, like at this part 1 was much better. Oh, I think I should be going because I have some things to do today. Okay, it's disappointing that we don't see parts like, why is it, what is it doing? If we say 2000, yeah, it's finding too many paths. Which is, but it's finding them quite fast. 5,000, it's weird, right? Like, no, it ends up, so maybe there is some scaling issue that starts to go like super, more than polynomial, and it just it's getting screwed. So yeah, it's taking too long. Let's not print this or not check that and see what happens. Like, what is the longest path that it finds with, I don't know, after K 6,000. Well, it's this path, which is quite more, quite larger than, almost double than what we had here. I really doubt that this is going to be the answer, but just to try something. That's not the right answer, it is too low. Well, yeah, bummer. But I guess like we are running into some like very combinatorial kind of problem here. Yeah, we're printing this start walk thingy, which I don't want to print. So let's remove this, but let's maybe take a look at the graph. Leave this thing at 1,000 and put this back. So the graph looks like this. So there aren't that many intersections in the actual input either. That's interesting. And most of these intersections like go to 2, well, it makes sense. It's either 2 or 3. It's either 2 or 3. So like the combinatorial nature of this, I don't know, to me it sounds like it shouldn't be that slow, like that freaking slow. But I would have to think about this more like with more depth. For now, let's leave this as is. Let's comment some of the noise. Like maybe let's leave it for find longest path, build graph. So we know now that the only thing that we need to do for part 2 is ignore this thing. So let's actually sketch out part 1 and part 2. So say graph for part 1 and graph for part 2. And this is going to be the answer for part 1 and answer for part 2. And again, just passing the corresponding graphs here. Beautiful. Answer 1 and answer 2. And what we want to do is ignore the slopes. So basically in part 1 the slopes are like, you have to obey them. So let's say if the x and slippery my cat is moving my computer. Come on, sit down and sleep. Slippery slope. If the slopes are slippery, we check this, and otherwise we just ignore them. So this and slippery slope, which is a Boolean. So for part 1 the slopes are slippery, and for part 2 they are not. Okay, so if we run this now with a sample, well, what's your problem here? Oh, I just wrote slippery slope. If we run with this, yes, this is now the expected output for part 1 and 2. And well, this is kind of a solution for, at least for the sample, for part 1 and part 2. But for the real input, it's still too slow. So next session, I think we're going to have to think about this find longest path, and probably not use this algorithm, this yen algorithm, for finding the k shortest path. Instead, we are going to have to do something custom, which I think shouldn't be that difficult to think about, but I don't know, because it's almost been 2 hours like thinking about walking this grid, and the code was really messy in the end. So yeah, let's commit what we have. Day 23, improve part 1 solution. Okay, and that will be it for this video. So as usual, if you have been, thanks for watching, and see you later. Bye bye.